This is D1, the sample paper. Let's just do it. So this sample paper is really weird. It asks you to do lots of descriptions of things quite a few times, and then they just didn't do that in the following up papers that actually existed. So that was weird. But anyway, describe a bubble sort. So you just compare the first two numbers. If the left is smaller because you're doing descending, you'll swap them. If not, you'll leave them. Then you compare the second and third number. You repeat. You go all the way to the end of the line, swapping them or not swapping them. And then at the end, that's the first pass done. Write something like that. Bubble sort is quadratic order, so we're going to take this number here, we're going to times it by this thing squared, divided by this thing squared, because of course quadratic. You could do this divided by this and then square it, that will be the same. However, for some types of order, that won't work so well, so maybe just do this idea, just do this applied to this, and then divide by this with this, and you'll get it every time. 2, a planar graph is a graph such that you can draw all the arcs such that none of them intersect each other. So yeah, cool. Hamiltonian cycle starting at A is just going to be, or you can just, I'm sure there are lots of them. I think I went for, okay, A, F, G, C, E, D, B, A. Okay, it goes through every point and arrives back where we started, so that will do. Now we add another arc here, taking the Hamiltonian cycle to just be this circle, I guess. Decide whether this is planar. So we'll write down every arc that's currently inside the picture, so that's AF, AE, AD, GB, and so on. There's 8 of them, I think. And we'll say AF needs to stay inside. We'll keep AF inside this picture here. Which means, of course, that GE, GC, and GB all need to be drawn outside. So like GE has to be drawn here to not cross with AF, which we're keeping inside. So those three we'll label as outsiders. And then we'll go through the outsiders we just wrote down. So BG is this one here. If that's an outsider, then anything it crosses has to be an insider. So AD and AE, will now, and AF, which we already said, have to be on the inside. Likewise with CG, so anything it crosses, which is BD and AD, which we already said, AE and AF, which we already said. And finally, E to G, which is this one, crosses AF, we've already labeled as an insider, so we get all of this, and that's all going well. And then finally, C to E, well, actually, what we should say is we've just said AE, AD, and BD are insiders, so AE is this one. I think that just crosses things that we've already described as outsiders. AD is this one, which crosses EC. We've labelled AD as an insider, so therefore EC must be an outsider. And everything is nice and consistent. You can go through it one by one if you want to, but everything is lovely and consistent. There's no contradictions, so therefore we can do a planar graph. You can even just draw the planar graph if you want to, although you don't have to. Question number 3 then. Start by deleting B's arcs here. So okay, I know first it says describe the difference between classical and practical. Classical means you need to go through every vertex exactly once. Practical means you're allowed to revisit and you have to do each one at least once. So that's roughly that. Starting and deleting B, so let's delete B and all of its arcs. Let's just delete those through and find a lower bound of the root. So we'll start at A, so we'll pick the shortest one that we can get to from A. Really, we should be reading this way, but it doesn't really matter. I'm pretty sure it's a symmetrical graph. But from A, the shortest one is F, so we'll include, sorry, no, it's D, 16, so we'll include that. And now we can pick things from either the A or the D row, and the next smallest is, I think, the one to A to F. And then we can pick from the A, the D, and the F row. I'm doing Prim's algorithm, by the way, to do this. Just seemed a sensible thing to do. So I think F to D, but we've already been to D, so that doesn't matter. The next shortest one is A to E, 21, for sure. So now we can look at the E row as well. A to C looks like it's 20. That will surely be the best thing to do. Next one will be C to G, which is 32. And the reason it's that is because we've been to every one now, except for G, I think. A, but we also haven't been to B, but that's because we've deleted it, of course. A, B, C, D, E, F, and then, yeah, we had to go to G. So go to G, and then, of course, you have to go back to A. Except you don't actually. I'll get to that in a second. So that's all the ways we can make a spanning tree, including everything except for B. And now all we have to do is take the two shortest arcs that join up B and add them in. So the two shortest arcs are this 17 and this 25. So let's get the total of these guys here, and then we'll add in 17 and 25, and we'll end up with that lower bound. There's no guarantee that will work, which is why it's a lower bound, but it's just a lower bound. Pretty found the nearest neighbor algorithms for A to C, so just do some nearest neighbor. We're going to do it again, I think, later on in the paper. So A goes to D, that's 16. Then D goes to, the nearest is F, so that's 19. Then F goes to A, which is 18, which we've already been to, so it's not going to be A, sorry, it's going to be E, which is 22. And then from E, again, we can't go to A, D, F, or E, which we're already at. So the next shortest will be C, I believe, at 20. And then from C, it looks like we'll go to G. And then from G, we, I guess, need to go to B, which the shortest way to do that is going to be this X here, because we just have to go to B. And then, of course, we go back to A, which is 17. And we end up with a total distance of that. And then we do the same thing from C, starting and ending at C. So C, shortest distance is 20 to E. And then from E, shortest distance is 21 to A, it looks like. And then from A, shortest distance is 17 to B. Oh, no, it's not, it's 16 to D. Did I literally say exactly that earlier on? I'm not sure. And then we go from D to F, it looks like, which is 19. And then from F, we need to go to B at some point because we haven't been there yet. And that's 31. And then if we still not visited G, and then F to G would have been bigger, so we go to B. And then from B, we go to G, which is X. And then we have to go back to A, which is 41. No, we don't. Sorry, we have to go back to C. What am I talking about? Back to C this time, which is 32. We add up all these results together, we get this. It says together those roots is 331, so we add up those two results and we get solve for X is 33. Write down the smallest interval. Well, this here is a lower bound, as we already said, so that's going to be the lowest bit. The upper bound is the nearest neighbor algorithm. So we're starting at A for this person's root. So we'll take this one and we'll put X is 33 into it, and we'll end up with this as our interval that we can say. Question 4 then, so it's going to ask us if Dijkstra's algorithm works, which it does. It's kind of like a trick question. You can do Dijkstra's on a directed graph. I think there's a past paper that actually makes you do that, if I remember correctly. Now we have to do Floyd's algorithm no fewer than 4 times. So we start with the initial table that they've given us. Now this is empty usually, but the easiest way for me to do this in PowerPoint is to just copy this table, and every time I actually have to replace a value here, I'll replace it here rather than just making them all come in. So okay, let's do this. So we keep A the same because we're obviously going through A. So B to C is currently 3. If we went to A, that would already take us 5, and then it would also take us another 11, which is 16, which is way bigger than 3, so we'll keep the 3 the same, like so much with the 2. When we're going to C to B, currently 3. If we go through A, that takes 11, and then it will take another 5 to get to B, so that's a terrible idea. So we'll keep the same, we'll keep this 4 the same reason. Now from D, we currently can't get to B, so going through A by going 8 and then 5 is 13 is a good idea, and we'll replace this with an A. And then B to C will be 4, that's big, it's smaller than 8, so we'll just keep it. And that's the first iteration done. Now we'll keep the B's the same. I've copied this table here, and again I'm just going to replace anything that needs replacing. From A then to C is currently 11. If we go to B first and then to C, that's 5 plus 3 is 8, so that's good. We'll replace that with a B. A to D is 8. If we go to B first, that's 5, and then we added a 2 to get to 7, so we'll replace that as well. C to A is currently 11. We'll go to B first, which is 3, and then to A, which is 8, so 5, so that adds up to make 8. We'll replace that, so lots going on here. And then I think that 4 will stay the same because it's 3 plus 2 otherwise, which is not less than 4. D to A is currently 8, D to B is 13, so that's not going to improve it, and neither is this 4. And that's our second iteration done, so I'll copy this table, and this is where we're at. This is the second iteration just done. Copy the table there, replace anything needs replacing. I'll keep the C's the same this time. A to B is currently 5. It's not going to help if you take 8 to get to C in the first place, and likewise this, so that's going to stay the same. B to A is 5 as well, so we could do a 3 to get to C, and then we could do a 8, but that makes 11, so that's not any improvement. The 2 is obviously not going to be improved on. D to A is currently 8. We could go to C instead, and then we could go from C to A, that makes 12. That's not an improvement. Again, D to B is currently 13. Go to 4, and then go to 3. That's 7. So that is an improvement. We'll replace this A with a C. Going through C is faster. That's the third iteration done. Copy this here. Keep the D's the same, and then I think 5 is not going to be improved. 8 could be improved if there was a 1 anywhere, but there isn't. 5, so we could go with 5, or we could go to D, which takes 2, and then we could go from D to A, but that takes 10, so that's not an improvement. This is not going to be improvement either. I don't think actually any of these will improve, will they? Does anything here improve? No, nothing improves. Good, cool, so we're done. I just completely lost patience with that. Explain how this can be used to find the shortest route from D to B. So D to B, the shortest route is 7, which I think I said. I did not say. I should say the shortest route is 7. Oh no, hang on, that's the distance. The root I have said. If you look in the table, D goes to, you want to go to B, but look in the root table, D actually goes to B through C. So okay, you're going to C first, and then you have to look at C and go, does C actually go straight to B? And it does. So if this has been an A here, you'd go from D to C, and then from C you go to A, then you go to B. But it doesn't. It's D to C, and then C goes to B, and then you're at B. So the root is DCB. And yeah, good. It continues, I think, it looks like. Use some more nearest neighbor, starting at D, to find the minimum root of going around everywhere. So starting at D, we're going to go to C, which takes 4. Then from C, we're going to go to B, which takes 3. And then from B, we'll go to A, because it's the last one to go to, which is 5. And then we'll go back to D, obviously, which is length 7. We'll add those results together. We'll get length 19. The actual root, again, using the table here, D to C is actually just going D to C. C to B is just going C to B. And then B to A is just going B to A. And then A to D is going through B. And B goes straight to D. So everything will be the same, except you're going to insert a B here. So you just do D to C to B to A, and then you don't go straight to D, you go back to B and then to D. And that will be the root. That's what the table tells you. Floyds and Dijkstras are applied to a network. Each will find the shortest distance. Describe how these results differ. So Dijkstra's, which I don't think we actually use in this paper, unless I'm forgetting. Dijkstra finds the shortest distance from one starting point to anywhere else in the graph. Floyd's finds all the shortest distances from everywhere to everywhere. So that's basically the difference there. Say something like that. Oh god, this question. So this is the whole question. Let's obviously get rid of the entire second half because it's not relevant. This took me a while to figure out. You've got 3 types of like hanging baskets, and each one is made of different types of plants, which is just ridiculous. I mean, I died inside while doing this question, I'm pretty sure. The garden centre can use at most 80 of those and those. Our profit is going to be 12S. S is labelled as X. D is Y. I mean, why they didn't just do S, D, and P? What? Anyway, I mean, I guess P is a bad choice because of profit, but we want to maximise 12 times X, 20 times Y, and 16 times Z. That's fairly clear. What's less clear is what the hell is going on up here. But what we can say is if we can use at most 80 impact plants, because Sunshine uses 2, Drama uses 3, and Peaceful uses 1, for every Sunshine basket you make, you use up 2 of them. So we need to keep 2 lots of X plus 3 lots of Y plus 1 lot of Z less than or equal to 80. And likewise over here, we need to keep 4 lots of X plus 2 lots of Y plus 3 lots of Z less than or equal to 140, and so on. And we end up with this. We also, of course, need X, Y, and Z to be greater or equal to 0 because we're making things, and they also need to be integers. And I think that's basically all of this done. Then it says simplex algorithm is used after one iteration, the tableau. Best thing about simplex questions is getting to say the word tableau. It is this. State the variable that's increased. So we just look at the BV column, which was RSY. It's now, it is RSY now. Initially, when you set this up, this would be RST. So this one's been changed. This T has been changed to a Y, so therefore the Y. You can also look in this column here. 001 means you've dealt with this as the pivot, so the Y has been changed. Determine how many plants in total are being used. So you've got 24 Ys. Now Y is drama. And if we look back, it takes, you can look in this column, or you can look back at the initial instruction. To make a drama, it takes 3 of these, 2 of those, and 4 of those. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 plants in total. We're making 24 of those things, so we're going to do 24 times 9, essentially, to get 216 plants in total. Explain why a second iteration of the simplex is... explain that this 2 is being used. So this is the most negative value in the profit. Going to work out some theta values, so this divided by this will ignore negatives. When I say we ignore negatives, we don't consider this a thing. We're looking for the least positive one. 92 divided by 2 is 46, 24 divided by half is 48. This is the smallest one, so we're going to pivot around here. And just maybe say some of that written down, but we're going to pivot here. Okay, and then it does that. It gets you another iteration done here. Use algebra to explain why this is optimal. So it's optimal because all of these are positive, but that's not really using algebra. So when you write this out, firstly, actually, I should say, this was really confusing to me. When we pivot from here, like I said before, when we pivoted in the initial tableau, they pivoted from here, and they changed this to a Y. Initially you set this up with RST and they changed that to a Y. So we just explained we would pivot here, and then they did it. So this should change to a Z, and they haven't done that, and that really confused me for a while, but that should be a Z. Anyway, explain why it's optimal. So all these are positive. When you write out the profit, that means P plus this plus this plus this equals this. And the reason this is optimal is because if you try to gently nudge X, S, or T upwards, P will go downwards, so therefore increasing any of them will decrease the profit, so therefore it's optimal, is what we want to say there. State the optimal number of each type, so we can say there's clearly one Y, which is one drama basket, and 46 Zs, which is peaceful baskets. And this is why, like, you might have thought, oh, you could decrease X, and that would increase the profit, but you can't, because X is currently at 0, so that's fine. The manager of the garden center is able to increase the number of impact plants from 80 to 100. So right now, when we... So, hang on. So impact plants is this expression, isn't it? We wanted to keep the impact plants less than 80, I think, if you read the previous thing. So this was the expression that we added R to make it equal to 80. R was the first slack, so it must have been given to this one. So this has a plus R equals 80. Now, if we increase the 80 to 100, that just means the slack will increase, and currently the slack isn't at 0, it's at 31. So the slack value will just go from 31 to 51, and so you'll have no effect on profit. You'll just, instead of having 31 random impact plants sitting around each week not being used, you'll have 51 instead, so don't do that. Question number 6, we're going to use this table to fill in. So we start with 0, 0. When we fill in the top rows, or top boxes, we're looking for the largest value we can find. So of course this just is a 4 because it's the only way to get there. This isn't a 5, it's a 4 plus 7, because what we're saying is the earliest these things can start is at 11. They can't start at 5 because you have to do this job and this job first, which takes minimum 11 to do. So that's the same idea we go on. So 4 plus 9 gets us to 13, and then here is 13 plus 2 bigger, or 4 plus 6, or 13 plus 2 is, so we'll go for a 15. And then down here maybe, which is biggest, 15 plus 4, 13 plus 5, or 11 plus 9. I think 11 plus 9 is, because I actually did this one first, because 11 plus 8 is 19, and then plus 0 is still smaller than the 11 plus 9 of 20. And then down here, the only way to get there is with a 21. A couple of ways to get here, either 21 plus 0, 19 plus 5, or 20 plus 4. They actually both equal 24. So that's the forward way done. We'll copy that number there, and then backwards, exactly the opposite. We're going to go for the smallest number we can get. Only way back to here is by taking away 4 to get 20. Only way back here is taking away 0, or here we can take away 5 and we'll get 19. Here we could either take away 8 or we could take away 9. So which one is the best thing to do, or gives you the smallest value? Well, actually they both give you 11, I think. But in any case, we'll head up here first, because that one only has one way of getting there. And then from here, which is better, 16 take 2, or 20 take 5, or 16 take 2 is lesser, so we'll go with that one. 14 take 9 is 5, 16 take 6 is 10, so we'll go with the 5 there. But actually, I already mentioned there should be 11 there, and then 11 take 7 is 4, so that actually gives you a 4 there. So again, just be careful to look through the whole thing and don't rush it. We'll end up with that. You can write down some working values if you want to as well, though I never bother. So that's there. It next wants us to do a Gantt chart or a cascade chart. So firstly, you want to put in the critical root, which is A, C, J, M, but also G, K. Those are both two divergent critical roots. So A to C is the same, and then we can go J, M to finish at hour 22, but we can also do G, K, and we'll have these two critical roots going on. Otherwise, though, B can start at hour 0 and takes 5 hours, but can finish as late as hour 11. So we'll fill in a grey block, finishing as late as hour 11. Then we'll go to D, which can start at hour 4, takes 9 hours, but can finish as late as hour 14. So that's an extra hour that it could finish, that it could be delayed by. A, B, C, D, E is the next one. So E is up here, 4 hours, starts at 4 hours, takes 6 hours, can finish as late as 16. So that's going to be quite a lot of slack time there, which we can just leave behind, or float time, I guess it's actually called, isn't it? A, B, C, D, E, F is up here. No, it's not F. Where's F? What is that? There it is. So it can start at 13, takes 2 hours, can finish as late as 16. So we'll start it at 13, takes 2 hours, can finish as late as 16, it's an extra hour. Then we'll keep going, we'll do the same thing. So H can start at 13 as well, takes 5 hours, slack time that takes you to 18, so another 2 hours to get to 20. And then we've only got a couple left, I think, at the end here. I is up here, can start at 15, takes 4, which takes you to 19, add an extra hour to get to 20. And then finally L, I think, is the last one, can start at 19, takes 2 hours, can finish as late as 24, so that's another extra 3 hours to finish up with. And I think that's my cascade diagram. Good, so I'll leave that there. It wants me to do a resource histogram now, so this is just a question of just filling in pictures. But anyway, resource diagram. So again, let's just start with the critical paths. So we'll just fill these along. Technically, I should have lots of separate A's here and lots of separate C's here. But if you've, I'm just telling you now, try doing this in PowerPoint and tell me that you're actually going to bother doing that. So I'm going to fill them in as solid blocks, and we end up with this. So again, the critical paths have gone in. B can start immediately and takes 5 hours. We're assuming everything starts at its earliest possible time. So B can start immediately, takes 5 hours. D can start at hour 4, so I'll put one worker there at hour 4, and then we can fall into this, and the second worker can do it instead. But that's only 1 plus 5. Is that, sorry, 6, isn't it? 1 plus 6 is 7, so there's still 2 hours left of D to do, because D takes 9 hours, so we'll put those there. E can start also at hour 4 and takes, how many hours? 6. So put one block there and then 5 blocks there. Just finishes short there. And then the rest of them are just these ones here. So F can start at 13, which is here, takes 2 hours. H can also start at 13, so put 2 of its hours there, and then the rest of the 3 down there. I can start at 15, which is here, so put 3 of the hours there. It takes another hour after that, so we'll just put 1 block down there. And then L can start at 19, and takes 2 hours, so we'll just fill that in there. So that's the entire picture. And now it says, is it possible to complete this with using only 3 workers? Now there's a couple of ways to look at this. One way is to think, well, L you can delay as late as possible and just fit in these last 2 boxes, which actually means you can fit I, all 5 boxes of I think, can just about fit in here. 1, 2, 3, 4, 5. Oh no, they can't. Can they? I is 5 boxes. Sorry, I is 4 boxes, of course, sorry. So yeah, if L goes as late as possible, I can just about squeeze into there. But then you've still got this H to deal with, and you can't move it much later. And even if you did, all of these rows are being used now, and you can't move it any earlier, so there doesn't seem to be anywhere to put any of those 2 boxes. The other way to think about it is just to say, well, nothing can start before this time, ever, aside from A and B. And now you've got 1, 2, 3, 4, 5, 6 hours of time that you'd like to sort of smooth out into this, but only 1, 2, 3, 4 blocks to put it in. So this is just absolutely impossible. So any explanation I think will do, but that could work there. Another simplex algorithm question here, because apparently they just hated us when they were writing this paper. Explain why simplex cannot be used here, because there's a greater than symbol. So good. Define what M represents. M is a very arbitrarily large positive real number, but it actually says use correct mathematical language, so M is a big boy. And then the next question says they've set up the tableau like this. They've set it up here. Explain where this comes from. So T1 comes from fixing this to be x minus the first slack plus an arbitrary, which they've called T, and then we can say it's equal to 3. And then you can just use the coefficients of this, the 1, the minus 1, the 1, and the 3 there, and you get this row, so that's fine. Explain where this row comes from. So P, you can write as this, but what you want to do is move all of this stuff over to the other side, and then say equals minus M times the sum of any artificial variables that you've added in, which in this case is just this T1. But you rearrange this T1 to be 3 minus this plus this, and then you rearrange this, and you get this, and then again this row is just the coefficients here, 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 and here, and we get that there. I've used S3 here, by the way. I could have mentioned I used S3 there because working downwards, S1 would have been added here, and S2 here, so I used S3 there. Good, so that's all done. And then it says you've got this tableau here, and they want you to do, they just want you to iterate this and get a solution. They actually put 4 tables in the answer booklet, which absolutely made me terrified that I would actually have to do this 4 times. But it turns out, as long as you don't make a mistake, you can do this in 2. So the largest negative here is this one, so we're going to do 19 divide 2, 12 divide 1, 3 divide minus 1. Again, we don't care about the negative one, so the smallest positive thing here is this one, so we'll pivot here. So we'll times this entire row by a half to get this, and we'll change this S1 for an S3, because that's where I'm pivoting around, that's what I fixed as a 1. So we'll change that out for an S3. And then of course we just need to make all of this bit 0 here. So okay, we do 1 1 minus 1, so this is a 1 here, so 1 minus 1 would give us 0. So what we're going to do is we're going to take this entire row and take away this row, which I've called little r1. So that'll give me a 0 there, and then of course 0 take away 0 is nothing. 4 take away 1 is 3. 0 take away 0.5 is minus 0.5. 0 take away 0.5 is minus 1.5. 1 take away 0 is 1. 1 take away 1 is 0. Minus 1 take away minus 1 is, sorry, minus, is this the t bit? Minus 1 take away minus 1 is minus 1 plus 1, which is 0. And then 12 take 9.5 is 2.5. So that's good. Then the next one down here, now this is a minus 1, so actually if I just add in this, I'll get to 0. So we're just going to add this in. So it's going to be 1 plus this 0 here, 0 plus this 1 there, 0 plus this 0.5, 0 plus this 0.5, 0 plus this 0, minus 1 plus this 1 gets you to 0, which is what we wanted. 1 plus this minus 1 also gets us 0, and then finally 3 plus this 9.5 gets us 12.5. And then lastly, to make this a 0 here, let's do this one plus 3 lots of this one. And similar sort of idea, we get to this eventually. 3 plus m plus minus 3 is just m. That's quite nice, good. And we'll have this. We've only got one negative left, so we're going to underline it and do some more values. So we're going to do 9.5 divided by 0.5, 2.5 divided by minus 0.5, ignore it because it's negative, and this divided by this. The smallest one is this one. So we're going to pivot here. So I think if we just take this entire row and times it by 2, and then put a z there, because that's where I'm pivoting now, then I think we're going to be in business. So times the entire row by 2, we're pivoting here, so put a z there. And now we can just say, okay, let's just sort out these, let's make all of these zeros. So okay, if I just do this one plus, oh sorry, that's the z, yeah, sorry. This one plus half of this one should get me to 0. So that's good, so I'll do this entire row plus half of this entire row here, which I've called R1 again. We get all these values. You can, 3 plus half of 2 is 4, and then these two match each other, so that's really nice for the most part. So yeah, and then 2 plus half of this, sorry, 2.5 plus half of 19 is just 12, and so on. And then the next one we're going to do this. I think just take away half of this will get us the right result. 0.5 take away half of 1 gets us to 0, and so we'll get the row there. You can verify my maths there if you want to. And then finally, same thing here, so minus 0.5, so same, whatever we did here will work, so add half of the of this one up here, and we'll end up with this stuff down here. And finally, all these are positive because m is a big boy, as we said. So we have the answers that p is 47, we have x is 3, we have z is 19. Now remember what these values actually mean. No, they don't mean anything. Good, excellent. So we have that. We have y is 0 because it's not one part of our basic variables column. So y is 0. And that will be the entire answer, I believe. Yeah, good, that's the whole paper. Thanks for watching, I'll see you next time.